All right, so one of the final topics we're going to talk about is Young's double slit experiment. This experiment is famous because it showed that light is wave-like, and the reason it showed that light is wave-like, one of the properties of waves is that waves can interfere with themselves. So what this guy did is he passed monochromatic light. Mono just means one, chromatic means color, so it's light of one wavelength, which is not the light, coming from the lights in our room here. Monochromatic light, it's like it's light with only one wavelength present. So he passed this monochromatic light through two slits, and then what happened is he saw this pattern appear on a screen, and the pattern was real simple: bright, dark, bright, dark, bright, dark, in both directions, okay? So the fact that light did that, the fact that light showed this pattern of bright, dark, bright, dark, bright, dark, showed that light can interfere with itself. So let's look at how waves interfere with themselves. All right, so wave interference. There's two ways that waves can interfere, and it's not just light. It's any waves: sound waves, ocean waves, light waves. So there's constructive interference and destructive interference. Constructive interference, so what does the word constructive mean? To build up, and then destructive is to break down. Constructive interference would be like this. We have wave A and wave B coming towards each other, and they're both at a peak, right? These wave pulses are both at a peak. Do they agree or disagree? Wave A and wave B. They agree. So when they meet, they add to each other, right? And then after they pass through one another, they go right back to what they were doing, okay? That's constructive interference. You got to know what that is to understand the double slit experiment. Now, destructive interference is when you have two waves that come towards each other, for example here, and they are disagreeing. Wave A is at a peak, wave B is at a trough, so when they meet here in the middle, they are going to what? Cancel, because they're out of phase. So they cancel here, and then once they pass through each other, they're right back to what they were doing. So constructive interference, waves add to each other. Destructive interference, they subtract from each other. Okay, now here is an example. This is from one of the multiple choice tests that we looked at. So we have two wave pulses, wave P and wave Q. Just these wave pulses traveling towards each other. And the question is asking us to figure out what these waves, what will be the shape of the total wave as wave P and Q pass through one another right here in the middle. As these two waves pass through each other, what are they going to look like? Well, hey, the best way to do this is break these waves into segments. So I'm going to just draw some lines here. Break these into segments. This will really help your brain. Okay, so we got segment 1, 2, 1, 2. So let's look at segment 1 for each wave. Segment 1 over here. Is this at a peak or at a trough? Peak. Segment 1 over here. Peak or trough? Peak. So what will the segment 1s do? Add to each other or subtract? Add. They're going to add to each other. Now let's look at region 2. Region 2 for this wave is at a peak, but for this wave it's at a trough. What will the region 2s do to each other? Add to each other or subtract? Subtract. So which is going to be the answer choice? A, right? That's how you do. It's pretty simple. It's, wave interference. All right, so moving on. Now, back to the double slit. Okay, so here's what happened. So the guy passed monochromatic light through two slits. Now notice this. Notice when the light waves leave the slits, they are in phase. Look at this. Peak, peak. They're together. See that? Peak, peak. Trough, trough. They are together. Together. All the way through to here, the waves stay together. Do you guys see that? It's like they're just like cruising along, doing the same thing like this, right? Do, do, My hands here are the waves. They're together. So, look, when these light rays get to the screen, are they going to add to each other or subtract from each other? If they meet the screen in phase with each other, are they going to add or subtract? Add, so we get a bright spot. Okay. Now let's go over here to this third diagram. Now look here. The waves start out together. Peak, peak, trough, trough. Peak, they're still together pretty much. Peak, peak. But then look, like right here. Right about here, like, whoa, what's going on right there? The bottom wave is at a peak. The upper wave is at a trough. Uh-oh. When they meet the screen, are they together or not together? They're not together, which is called out of phase. They are out of phase with each other, so are they going to add or subtract? Subtract, and we get a dark area. Is this making sense? Now, look at the next thing I'm going to say is the key to understanding this double slit experiment. What is the explanation for how these waves got out of phase? They started in phase, but then they got out of phase. I'm just going to tell you. The explanation lies in the fact that the waves are traveling a different distance. So this upper wave here is traveling that far. The lower wave is traveling that far. So which ray is traveling farther? The top ray or the bottom ray? The top ray. Now, dudes, am I saying that whenever you have a ray that travels farther, it's always going to be out of phase? No, because look at this middle one right here. Top ray, bottom ray. The top ray is traveling farther, but we get a bright spot, right? So look, the key to the double slit experiment, it has to do with the fact that one of the rays is traveling a farther distance. Okay, so let's go to the next screen. So here's a geometric look. Here's a geometric look at the double slit experiment. So look, if you're on track for a 5 and you're going to learn this, the variables are really important. D is the distance between the slits. L is the distance from the slits over to the screen. And then Y is the distance from the center line between the slits up to the point you're focusing on. Now, what's this point that you're focusing on? It could be a bright spot, could be a dark spot. It depends upon what you're doing, okay? But Y is the distance from the center line up to the point you're focusing on the screen. And then lastly is theta. Theta is the angle, so we'll look at this triangle right here. So see this blue triangle? Theta is the angle from the midpoint between the slits up to the point you're focusing on. That's theta there. But then theta also appears in this smaller triangle right here. This, what color is that? Like yellow? No, brown. I'm colorblind. This other smaller triangle. This is theta right there. Okay? Now, we have 2 rays. We got ray 1 and ray 2. Which ray is traveling farther? So ray 1 does that. Ray 2 does that. Which ray is traveling the farther distance? Ray 2. How much farther does ray 2 travel? It is this distance right here. Shh. This distance right here is the extra distance traveled by ray 2. In order for point P to be a bright spot, if point P is going to be a bright spot, or what they call a fringe, a bright fringe, what has to be true about the extra distance traveled? It needs to be equal to a whole number multiple of the wavelength. It's got to be exactly 1 wavelength, or 2 wavelengths, or 3 wavelengths, and so on. 4 wavelengths, 5 wavelengths, and so on. Does that make sense? Okay. If point P is going to be a dark spot, what they frequently call a dark fringe, if this point is going to be dark, what has to be true about this extra distance traveled? it's got to be what I call a 0.5 multiple of the wavelength. So it's going to be either half of a wavelength, or 1.5, or 2.5, right? Can you guys visualize this? You got to think about these waves as almost like they're Legos, you know. If the extra distance traveled happens to be an exact multiple of the wavelength, they are going to be in phase when they hit the screen. Now, d sine theta, where does d sine theta come from? Look, if you focus on this smaller triangle right here, so theta is this angle right here, so let's just look at sine theta. So sine is opposite over hypotenuse. What's opposite that theta? Opposite the theta is going to be the extra distance, right? The extra distance traveled by ray 2, and then what's the hypotenuse for that little triangle? D. So if you rearrange that, what's this extra distance right here? D sine theta. D sine theta is the extra distance traveled. If it's equal to a whole number multiple of the wavelength, you get a bright spot. Now, in these equations here, this is what I talked about. If d sine theta equals a whole number multiple of the wavelength, so look, m is referred to as the fringe order. This is called the fringe order, which I'll explain later. That's the fringe order. That's the 0, 1, 2, 3, 4, and so on. If you're going to get a dark spot, it's going to be m plus 1/2, a 0.5 multiple. All right, we're almost done, guys. Almost done. Okay, final thing. So same diagram. They could ask you to calculate where these fringes will appear, you know, measured from the center line. So that's y. Now, how are we going to solve for y? I'm going to show you. What we're going to do is this. We're going to take the equation from the previous screen, which was d sine theta equals m lambda, where m is the fringe order, 0, 1, 2, 3, and so on. Now look, sine theta, so focus on this blue triangle. Focus on the blue triangle. Sine theta can be approximated to y over L. So look, theta, here's the theta right here. Here's the angle right here. What's sine? Opposite, which is y, no problem there. And then why the heck am I saying the hypotenuse is L? Because sine is opposite over hypotenuse. So what we're doing is we're approximating this hypotenuse to be L. Now, why can we do that? The reason we can do it is because theta is small. So look, I'm going to make a triangle here. I'm going to make a triangle. Boom. 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 There's a triangle. Look, if your theta is small, if the angle of the triangle is small, wouldn't the hypotenuse pretty much be the base? Yes. So it's an approximation. So take this sine theta equals y over L, plug it in right there, and what you're going to get is this equation here. So to calculate where a bright fringe appears, one of the bright spots, measured off this center line, you go lambda L over D multiplied by the fringe order. And then if you want to calculate where a dark one's going to appear, it's the exact same equation, just change the m to m plus 1/2. Okay? Now, very, very final screen. Promise. So those m's, look at. So the m's, just understanding the m. Like if they're talking about the first order bright. First order bright means m equals 1. So that's going to be, we're always measuring off this center line. The first order bright is this guy right here. So look, your y would be that. If you're calculating where the first order bright is, what you do is you plug in m equals 1 into the equations we were talking about. Bam, you'll measure y right there. What if they're talking about second order bright? Second order bright would be this second bright right here. This dude right here is m equals 2 for bright. The only tricky thing here is that there are two 0th order darks. This guy is called the 0th order dark, and then this guy is the 0th order dark. That make sense? and the pattern going up is the same as the pattern going down. All right? That's the double slit experiment.